In Module A3, Objective 9, we're going to look at the effects of exercise hormones and nutrition on bone development. We see that turnover and recycling of the minerals within the matrix give each bone the ability to adapt to new stresses. Because of this adaptability, because bones are so adaptable, their shape often reflect the forces that are applied to them. For instance, here in this little diagram, we have the deltoid muscle. And the deltoid muscle is your shoulder muscle. And it connects to the humerus right here onto a little ridge known as the deltoid tuberosity. And that's denoted in this picture as D, the deltoid tuberosity. And again, we see this little ridge that sticks off the shaft of the bone. And again, this is where the deltoid muscle attaches. When an individual stresses that deltoid muscle, when either they utilize their shoulder muscles repetitively and in some type of job, or whether they're pumping iron at the gym, what happens is not only does the deltoid muscle increase in mass, become more pronounced, become larger, stronger, but also the deltoid tuberosity also increases in size. So this is what is meant by stresses applied. When the deltoid muscle contracts, it pulls on the deltoid tuberosity, and that's going to lift the arm. So that stress, in a repetitive sense, causes an increase in the size of the deltoid tuberosity. Likewise, we find that muscles with decreased activity often lose or causes the loss of some of the bone mass. This bottom picture is an individual who had broken a bone in the leg somewhere, and they've been restricted. They probably wore a cast for some amount of time. And what has happened is the leg musculature has atrophied. It has decreased. It had lost mass. And this is a good picture because it compares the right versus the left leg, and you can see that the patient's right leg is considerably smaller than that of the left. So the muscle mass is decreased. Along with that decrease in muscle mass, we can also anticipate a decrease in bone mass. The bones hold articulation sites for those muscles, and as the muscle is immobilized, the stresses are not present, and the bone mass is lost. They say that over 3 weeks, a third of the bone mass could be lost. And of course, once that cast comes off, the leg is weak, but through therapy, through physical therapy, the muscle mass and bone mass can be recaptured, so to speak. So what is needed for normal bone maintenance in terms of growth and repair? Well, obviously we need a source of dietary calcium and phosphate salts. Okay, calcium and phosphate salts are the main constituents of the bony matrix, and in order to help build bone mass, we're going to need those salts. Together with those two salts, we also find that minerals like magnesium, fluoride, iron, and manganese are also required, just in smaller amounts. So once we increase the dietary intake of calcium and phosphate salts, we need to find a way to get those minerals from the digestive system into the bloodstream. And that is aided by the hormone calcitriol. Calcitriol is a hormone that is produced in the kidneys, and it helps with the absorption of calcium and phosphorus across the digestive tract into the bloodstream. Other substances that are needed for normal growth and maintenance include vitamin C. Vitamin C is important for collagen synthesis, as well as for the stimulation of osteoblast differentiation. What will an osteoblast differentiate into? Osteoblast is going to differentiate into an osteocyte. Vitamin A stimulates osteoblast activity. So osteoblasts, if you remember, they start producing the uncalcified matrix. Vitamins K and B12 are important for the synthesis of certain bone proteins. We have a couple hormones, growth hormone and thyroxine, which is a thyroid hormone. They help stimulate bone growth. We're going to look on the next slide at what happens when we have mishaps with growth hormone. Estrogens and androgens help stimulate osteoblast activity. And lastly, we'll look at the calcitonin and parathyroid hormones. These two particular hormones are antagonistic. And we'll define this term later as we look at their activity, but I just want to get that out there now so you can start thinking about it. This is figure 614 rather, examples of abnormal bone growth from your text. And in figure A, we're looking at basically pituitary dwarfism. This is due to an inadequate production of growth hormone, which is ultimately going to lead to reduced epiphyseal cartilage activity and abnormally short bones. So one hormone, the production of one hormone, can affect bone growth to this extent. On the opposite end of the extreme, and you don't have this in your in your book, I pulled this off another source. This is pituitary gigantism, and this is due to an overproduction of that same hormone, the growth hormone, prior to puberty. So before those epiphyseal plates closed, the hypersecretion again refers to increased secretion. The hypersecretion of growth hormone caused those long bones to grow considerably above that of a normal individual. This was Robert Wadlow of Alton, Illinois, who eventually died at about the age 22 at 8 foot 11 inches tall. So this is just one or two extremes. But again, both of these were caused by just one of those elements being out of whack.